Hi everyone, this is session 4 of program 1 and we're doing geometry again. So let's get started. So basic rules, I think we're all aware. And a reminder that course content will be uploaded, and feel free to join the Discord server. Okay, so there are a few things that we're going to go through today. Firstly, we're going to go through cyclic quadrilaterals. Secondly, angles at a center, which is a theorem. Thirdly, angles from the same arc, subtended from the same arc. And then fourthly, tangents and alternate segment theorem. Okay, so cyclic quadrilaterals. Is anyone familiar with what a cyclic quadrilateral is? Feel free to message me or raise your hand and unmute yourself, any of that. Awesome. Do you want to share with the class what a cyclic quadrilateral is? You can type it in chat or you can unmute yourself. But you don't, yeah. So, a cyclic quadrilateral, the vertices of the quadrilateral can fit in a circle, so they all lie on the circle, and opposite angles add to 180 degrees. Awesome. So, this is like basically what a cyclic quadrilateral looks like. So the 4 cyclic quadrilaterals on the left-hand side, those ones, you can see that all the vertices are lying on the same. And this circle is called the circumcircle, or the circumscribed circle, which we also discussed last time when we were talking about triangle centers. So out of the ones on the right-hand side, can someone tell me which one is not a cyclic quadrilateral? Just to see if everyone kind of understands what it is. Yep, good job, Jackie. Anyone else? Okay, I'm not getting any other messages, I don't think. Oh, am I? Oh yeah, good job. Okay, so it looks like we've basically got the gist of it. Yeah, good job. So the answer is A, right? Because you can see those 2 points aren't lying on the same circle. Okay, awesome. So let's talk about angles at the center. So there are a lot of really important properties of cyclic quadrilaterals that are really useful for doing proofs and angle chasing. So angle chasing is when you kind of use a sequence of logical steps to get to like find out what one angle is like in relation to other ones and prove certain properties. Yeah. Okay. So angles at the center. So I'm giving everyone an exercise. It would be great if we could all give it a try. So I want you all to prove that the angle at the center of a circle is twice that of an angle at the circumference when subtended by the same arc. So what I mean by that is in the diagram, we can see there's like a smaller angle labeled theta, and we want to prove that the angle from the same arc, so we can see, the 2 other points opposite the angle that touch the circle, that defines the arc. And then we want to prove that the angle going from there to the center is double. Okay, so do we all understand the problem? Okay, awesome. Someone's already gotten it. But for the rest of you, then how about we let's just take, until 8:10 to just give it a try. I think that yeah, it mostly just uses basic geometry properties that we probably already know, so it'd be really good if we could all give it a try. And I'll give a hint at the 2-minute mark. Okay. Yeah, so you can all give it a try. And let me know if you have any questions. Okay, so I'll just give everyone a hint. One thing that we can do just for approaching the problem is draw an extra line in. So, Jackie, do we want to share with everyone what that line is? You can type it in the group chat if you'd like, or say it out loud.
Well, I added 2 lines. Well, yeah, so first one I added was this one. Wait, sorry, it's not working. Oh, yeah, that. And I also added that one.
Awesome, awesome. Yeah. So thank you so much, Jackie.
Okay.
What that does for us is it creates a couple of isosceles triangles, because note that the line that Jackie created, the one that goes from the center to the point that has angle theta, is also a radius of the circle, which means that those 3 lines that come out from the center are all equal, and we get quite a few isosceles triangles. So we can use the properties of isosceles triangles to solve our problem. Yeah, so just hopefully keep it going, and then, yeah. Okay, it looks like our time is up now. So has anyone else gotten it? Okay, Vinny, thanks for showing me. Okay, nice try, nice try. It's looking like a good diagram. Okay, so anyone else? Or... Okay, yeah. So one solution that I just received was when you kind of construct a particular triangle, right? So you kind of like draw your diagram the way you want it, and then you assume that certain angles are like going to be certain numbers. And I think that's like a really good intuitive approach. The next step, I think, would be to kind of prove that this is true for every single circle and every single little triangle that you draw as well, for any kind of angle. So I'll share my screen and then we can go through this. Okay, can everyone see my screen? Oh dear, not my Apple Pencil again. Okay. Anyways. So what we want is to show that this is true for not only for a specific case, but that it works for in general as well. So what we can do is just by noting firstly that the sizes of the angles that we choose are basically arbitrary. So let's just draw this all out. So we can pick a point on the circumference. And then, of course, I think it'd be good to label as well. So, and we have center O here. So what we wanted to do is draw these 2 lines to make it quite clear that we now have isosceles triangles. And then why we want to do this is because I feel like this problem isn't giving us like that many properties to start with. Like the main focus, like the main information we have is just like the different radii, right? So we just want to know that these are radii. Okay, now what does that mean? In an isosceles triangles, in an isosceles triangle, we have two angles that are going to be equal, right? So let's assume that this one, angle BAO, equals to x, okay? And then that angle CAO equals to y. So I'm just going to label it as x and y to make things kind of simpler to write out, maybe a bit simpler to look at sometimes. Okay, now because triangle AOB and triangle AOC are isosceles, and we all know why they're isosceles, right? Because they're radii. So we have two sides of the same length. And because of that, we also have these angles that are equivalent as well. Okay, does that make sense so far? Any comments from anyone? Okay, awesome. So it's making sense. That's good. Okay, so the next step is we kind of have to just, well, since we've written out the angles that we do know, we want to do like a bit of, I guess we want to write it out a bit more so then we can see how things are all going to match up. So what we know is that angles in a triangle add to 180 degrees, right? So what that means is that x plus y, which would be a, plus b, so which is this other component, let's just call this z for now. Sorry. Plus z, which would be b, plus y plus z, which would be c, equals to 180 degrees, right? And then if we just write this out more, we get 2x plus 2y plus 2z is going to equal to 180 degrees. Okay. Have we all got that? You can use algebra and draw triangle in the circle. Yeah, sorry, that was from ages ago. I didn't see that because I'm on like 2 accounts. Okay. Yeah, okay. So we're going to prove now that our angles are going to be double at the center. So how do we get to that? Right now, we have kind of used the bigger triangle, like the one that that has all three vertices on the circumcircle. And we have this little equation here, right? And then now we wanted to consider the smaller triangle, this one, yeah, the one that is at the center. And then what we want to do is consider once again, because it's a triangle, the angles inside are also going to have to add to 180 degrees. So now we can construct a second kind of equation. And then we get 180 is going to be equal to 2z, right? Because we have this angle here and this angle here, plus the angle at O, which would be angle BOC. Well, we know from the previous equation that 180 equals to 2z plus 2x plus 2y. Now, what does that mean? That means that BOC equals to 2x plus 2y. And then now we can just compare it to the angle BAC, right? Which is the angle at the circumference. BAC equals to x plus y. So therefore, BOC equals to 2 times BAC. Awesome. Do we understand that? And also, I think that, like, when you're laying out a proof, you want to make sure you kind of go through all the steps. I might have maybe missed a few steps, but I think most of the important ones would be here. And when we're making a proof, we also want to show that unless it's specified, when you're given a problem like this, you want to prove that it works in general as well. Okay, so I think we can stop there and then go back to the slideshow. Yeah, okay, so good job to everyone for your work, and thank you to those who contributed in the chat as well. So now we'll move on to the next property, super important as well. So this is angles from the same arc or angles subtended by the same arc. So an interesting result is that angles subtended by the same arc are equal. So I'll just talk through what is illustrated in the diagram. So an angle subtended by arc CD that goes to point A is going to be equal to half the angle at the center that is subtended by CD. So I think I'll draw this out again and go through the process, but this is just an explanation first. And then similarly, an angle subtended by arc CD that goes to point B on the circumference is equal to half the angle at the center that is subtended by CD at the same arc. And because of that, the two angles are equal. So this is essentially using the same property. But what is subtended? Really good question. So subtended basically just means that it's the arc that goes across those points. So I'll just share my screen and then, of course, we can go through this in a bit more depth. Okay. You can see my screen, I hope. Okay. Oops. Okay. So when we have an angle subtending an arc, we're referring to the arc that might be like this, right? So say we have an angle. Oh, that's not nice. Say we have an angle here. Then the arc that it's subtending will be the one here, right? And then similarly, like if we had an angle here, and it was this angle, then the arc that it's subtending would be here. And what it means to subtend the same arc is that essentially it's coming from the same part, right? So you have this arc AB. We're going to have another angle that's also subtending it. So then we go like this. So any arc that kind of comes from this arc will be equals. So these two things, let's like that. These two are actually equal. Right. So is that clear as to what subtended means? Okay, awesome. Also, just for anyone who is messaging me, since I'm sharing screen, I can't see the chat on my iPad. So it'd be good if people could message the MINDNZ account rather than Nicole. Okay, cool. So we want to leverage the property that we just proved right before to show that these things are actually equal. Okay, so I think it's pretty, my pencil, very pleasant. Okay, so the thing we want to do is show that one is equal to half that at the center, and it show that the next one is similarly true, and then thus they'll be equivalent. So look, we have this here, the angle at the center. Let's call this 2 theta. Then we know that any other angle here that also comes from the same arc, but kind of lands on the circumference, will be theta. And that applies for any angle that subtends the same arc, regardless of where on the circumference it is coming from. So that means that these two are both going to equal to theta. And thus they are equal. So that's just kind of the proof. We compare the red one to the black one, and we compare the blue one to the black one, and then show that they're the same by comparison. Does that make sense? Okay, well, then, okay, sort of. Okay, sure. Right, so what we want to remember is just that angles subtended by the same arc are equal. So we want to just kind of consider one circle like this. Then we have, let's just suppose we have a certain angle here. And this is the arc that it's subtending. Okay, this is the arc that it's subtending. And let's just assume that this is theta degrees, right? It's just like a number of degrees. It could be any kind of thing. It could be like 30, it could be 60, 49, something like that. Okay. And then what we're saying is that any angle that comes from the same arc will be equal to it. So that means that this angle is also going to be theta. This angle is also going to be theta. So there are going to be infinitely many angles that are also equal to theta. Yeah. Okay, does that make a bit more sense? Let me know if you need anything. Okay. Oh, awesome. Okay, cool. So why is this so useful? I think the applications of this a lot of the time are for cyclic quadrilaterals, which we talked about just before, right? So we have a cyclic quadrilateral, and I think it's a good idea to inscribe this in a circle a lot of the time. Okay, let's call it A, B, C, D. So what we're going to do is we're going to connect the opposite parts. Okay, let's just do a quick exercise. Can anyone tell me which angle BAC is equal to? So remember, angles that subtend the same arc are equal. Here, angle BAC is subtending the arc BC. Oh, that's, ew, gosh. Yeah. Can anyone tell me which other angle also subtends this arc? Awesome. Really good job. Really good job. So one person's got it. Does anyone else want to share with me before I say the answer? Close, but I think we want to think about maybe just switch up the order of your letters. Might be looking at the wrong angle. Okay. Yeah, nice, nice. Good job. What's the question? So we're just trying to find out which angle BAC is equal to based on which arc it's subtending. Okay, so BAC subtends arc BC. So we just want to find another angle that also subtends the same arc, and that would be our answer because they must be equal. Awesome. Okay, really good job, guys. Yeah, that's really, really good. So our answer would be angle BDC because it's also subtending the same arc. It also comes from the arc BC. Okay, really good job. So let's just do another practice quickly. Let's just say which one is the same as angle DBC. Awesome, awesome. One person's got it. Not quite, not quite. I'll just draw out which angle it's subtend, which arc it's subtending. So DBC, DBC, we get this arc over here. Okay, now we just want to find something that is also subtending that arc. Yeah, nice, nice. Really good job. Okay, I think we can just say it now because I think most people have gotten it. If you haven't, don't worry about it. I think because someone has, yeah, I think we seem to have sufficient understanding. So look here, we have angle DBC that is coming from this green arc. In a similar fashion, we also have this one, which is angle CAD, which is also subtended by the same arc. And therefore they are equal. Okay, so do you think, does everyone think that's pretty clear? Okay, awesome. So I will just quickly share again. And this, I think, that I want to show with regards to this that I think is really useful. Okay. So what we want now is to show that opposite angles in a cyclic quadrilateral are supplementary. So this is what someone told me early in the session when they were defining what a cyclic quadrilateral is. So I think it's something that might be pretty useful to prove as well. And a good way to do this is to use the result that we just proved right before, right? So we can just kind of label the angles and then see how it plays out. How about everyone take 2 minutes to give it a try? Oh, someone's already got it. I use the rule we learned the angles at the center. Oh, that's a good idea as well. Yeah, really good. Yeah, there are definitely quite a few ways to do it. The reason why I'm suggesting that we use angles at the same, subtended by the same arc is just because we went over it just before. So I'm trying to kind of build up so that we can do some problems later on in the session. But it's up to you how you do it. For every proof, there are so many options as to how you can approach it. So yeah, really be creative. Don't be afraid to try things out. So you can just take 1 more minute and then I'll talk through the solution. Okay, has anyone made any progress? Okay, well, I think that we can just go through the solution then. Okay, so what we want to prove is that angles, opposite angles in a cyclic quadrilateral are going to be supplementary. In other words, that they add to 180 degrees. So I think there's a really straightforward way of approaching this. If we just keep on applying the same property that we learned just before. So here we have a cyclic quadrilateral. Okay, so let's just first say we're going to try to prove that angle BAD plus angle BCD equals to 180. So how I'm going to approach this is just by labeling all the different angles we have. So this angle will be equal to this angle because they're subtending the same arc, DC. This angle will be equal to this angle because they're subtending the same arc, BC. This angle will be equal to this angle because it's subtending the same arc AB. And then finally, this angle will be equal to this angle because they're subtending the same arc AD. So now what we know is obviously, well, in a quadrilateral, the angles are going to add up to 360 degrees. So let's add all of this up and see what we get. We get A plus B plus C plus D equals to 360. And then if we write that out, X plus W plus Z plus W plus Y plus Z plus X plus Y is going to equal to 360. Now, 2 times X plus Y, oh, I'm missing the W. W plus X plus Y plus Z equals to 360. And if we divide both sides by 2, then we get W plus X plus Y plus Z equals to 180. And that's really interesting because W plus X equals to angle BAD. And then Y plus Z equals to angle BCD. So then we can just put it together to show that this is true. Then we just get BAD from W plus X plus angle BCD from Y plus Z equals to 180, as we tried to prove initially. Okay, does that make sense to everyone? I think that this is a pretty simple way of doing it. We just kind of have to write everything out and then it all becomes clear. Okay, really cool. Yeah. So now back to the presentation for a few last section. All right, so the last thing that we're going to talk about would be tangents and alternate segment theorem. So we talked a bit about a tangent, what a tangent is last time, I'm pretty sure. So let's just do a quick recap. A line that touches the circle at a single point is tangent. So the point where the tangent meets the circle is called the point of tangency. And what the tangent does is it intersects the radius of the circle and is also perpendicular to it. If two tangents are drawn to a circle from an external point, then they are the same length. So here's an exercise. AB and AC, as pictured in the diagram, are tangent to the circle. A is a point outside the circle. B and C are the points of tangency. So what I want you all to do is prove that AB equals to AC. So how about we take 2 minutes to do this? And could we add a line from B to the center and C to the center, then say that it is. Yeah, okay, I'm not going to say the rest of that out loud since that's basically the whole proof. But yeah, that's exactly right. That is just how we do it. Good job. Okay, I think we can probably just go for the solution for this now. So I will go and share my screen. So yeah, I got a really good proof in chat before. So I'm basically just going to do the same thing. Oh, not a circle. Okay, so here we have a circle. Let's suppose we have a point A. And then the tangents. Yeah, okay. B and C. Oh, that's not. Okay, C are the points of tangent C. So we want to prove that AB equals to AC. Okay, so how do we do this? We use the very important property of tangents, which is that they are perpendicular to the radius. Okay, now that's really interesting because now we get these 90 degrees. And also, we can draw a line here from A to the center. Okay, now what we notice now is that it looks like these triangles, these two triangles, A, B, O, and triangle A, C, O, they look really similar. In fact, I think they're congruent. So why is this? Firstly, we can see that they both have they both have 90-degree angles. Secondly, they share a same side here. So AO is a common side. Specifically, it's the hypotenuse of both triangles. And also because this is in a circle, BO and CO are both radii, and thus they are the same as well. So now, what do the two triangles have in common? They have these three things. They have a right angle, they have BO equals CO, and they also have AO equals AO. And therefore, the two triangles must be congruent, and then AB must equal to AC. And we hopefully remember what congruent means. Okay, so does everyone kind of understand that? Okay, awesome. Does anyone else have any input? It might be a bit too much to, yeah, it might be a fair amount to process at first, but we just really want to keep in mind certain important properties, like the tangents being perpendicular to the radius. And then we just want to make sure that we know how to apply them. Yeah. Okay. So then we can move on to alternate segment theorem, which I think is fairly interesting. Okay, so here we have alternate segment theorem. So in a circle, okay, the sentence is a bit wordy, so I think it might be easier to understand if you just look at the diagram. So just note here that the angles that are colored using the same color are equal. So in a circle, the angle between a chord and a tangent through one of the endpoints of the chord is equal to the angle in the alternate segment, which is the angle subtended by the chord in the opposite side of the previous angle. So we have like the pink angles, they're equal, the green angles, they're equal. So can someone try to prove this for me? If anyone already knows, feel free to share. If not, let's just take, how about we take 3 minutes to try figure it out. Okay, yeah. One thing that is pretty helpful would be the property that a triangle is 180 degrees and the line is also 180 degrees. Good job, Jenny. Okay, I got a solution, but I don't really know how to explain without drawing it. Yeah, I get that. It's pretty hard to explain, especially when you're trying to like label things as well. But yeah, really good, really good. So something we want to pay attention to is the property that the tangent is perpendicular to the radius line. And then isosceles triangle. Yeah, really good, really good. Yeah, sounds like you got it. Okay, I think I know what you mean because you're hitting all the steps. But yeah, one thing that I might do for when I'm explaining this is kind of try to write up like a cleaner proof so we kind of get an idea of what points we want to hit and how we can explain our ideas pretty clearly. Choose a common angle. Okay. Yeah, I guess it's like when we're talking about geometry solutions, it's kind of hard to kind of like, just type it out because it's a lot easier to see visually, right? When we all draw different diagrams and things like that. But it sounds like, from what I'm seeing in chat, it sounds like we're getting it. So it's, yeah, that's good. So I think we can go over it now. So I'll share my screen. And as always, feel free to message me if you need me to slow down or go over anything extra. Okay, and also another thing to note, as always, is for one problem, there can be a lot of different solutions. So yeah, don't be deterred if mine isn't the same as yours. This is just like probably one particular one that I'm giving. It doesn't necessarily have to be like this. Okay. So I'm not really sure about, I mean, we can really label the points however we want, right? So I'm just going to label the ones in a triangle first. I don't like the look of that. Okay, that's better. This triangle's a little slightly weirder. Okay. A, B, C, and let's just call this D. So I think one thing that is pretty interesting is since like the property is the same regardless of whether you do like the pink or the green angles shown in the diagram, the proof will be the same. So then we can just really do it for one side. So what we want to do here is prove that this angle DAB equals to ACB, this angle. Okay, so I think someone seemed to have a really good idea of how to do this before with an isosceles triangle. So, how do we construct this? Can someone tell me? Like, which parts do we use to make the isosceles triangle? I'll just check my messages. Okay, yeah, a center C. Nice. Wait, a center C? Uh, mm, wait, what do you mean by a center C? Is it just like AOC? Yeah, okay, cool. Okay, so we want to note that AO is going to be perpendicular to this tangent line. Okay, nice. So, the isosceles triangle AOC. I think for me in this case, wait, did you like do it the opposite way around? Oh, do you want to try and explain? Yeah, good idea. Okay. Do you want to just like do the annotation? Okay. Cool.
Wait a second, I can't seem to like draw on it.
All good, take your time.
I don't think there's like that drawing thing I can do anymore.
Oh, the
Oh,
white. Oh,
yeah, whiteboard.
oh, really? Oh,
Oh, well, I meant like from AC, that
mm-hmm.
line, and then if I continue AD, I meant like that angle, the other side.
Oh, the other side. So in this case, would we just make it like A AOB, like just to like mirror it? Is it like the
Um,
same as that, but like kind of just reflected the opposite way around? Or
not
okay,
really.
oh, should I just change it the other way around then? So like, do you want this angle to be like um this angle instead?
Yeah,
Okay, and then okay, so we can just do it the other way around as well. It doesn't really matter. Okay,
yeah.
so
Okay.
what we want instead is that we want oh yes, and I'll move D to the other side. So we want DAC to equal to ABC. Okay, so then what you were saying was we want to have the isosceles triangle AOC. Okay. Oh, and then is what you did kind of just like subtract, like
Yeah,
subtract
well,
this.
I said that. Well, no, well, I said that I mean, no, OAC is like 90 minus X if CAD is
Mm,
X.
nice. Yeah. So we can just call this X. This part is a little small to be honest, but let's just
Mhm.
draw an arrow then. Let's call it 90 minus X. And we know that because OAD is 90 degrees. Okay, then what's next?
And then I said that OCA is 90 minus X because it's an isosceles triangle because all of it's a radius.
Yep, nice. So we want to know that. We want to just note that OC and OA are the same.
Mhm.
And then,
And then COA would be 2X because angles in a
mm,
triangle add up to 180.
awesome. Yeah. Okay, I'll just change the color. And this would be 2x. And
Yeah.
then,
Using like the first rule we learnt, A, B,
yeah,
C is X.
nice. Really good job. That's such a good proof. So what we've gone through there is gone through like a bunch of logical steps, and then we show that these are equal. Does everyone kind of understand that? Because we're kind of just using properties that we've been through mostly today. So I understand if it's like a bit hard to suddenly try to apply. But yeah, that was a really good proof. Thank you so much. Does everyone kind of understand this stuff? Because essentially we just use a lot of different properties and try to put it together. And it can kind of get a bit confusing, but we just want to make sure that we are processing every step. Mm, no pressure to necessarily, say anything, but feel free, of course, to tell me how you're feeling if you want some extra explanation.